So from this lecture onwards, we will focus mostly on what are called linear differential equations. In this, we would start by looking at first order linear differential equations. However, it is useful to know what are linear differential equations in general. So let's define what is a linear differential equation for an nth order ordinary differential equation in a dependent variable y of x and an independent variable x. As we know, an nth order differential equation would involve nth derivative of y with respect to x as its highest derivative term. If it's a linear nth order differential equation, it will have its highest derivative given in terms of the lower order derivatives such as dn minus 1 y by dx n minus 1 and d n minus 2 y by dx n minus 2 etc. dy by dx as well as y itself So the nth order derivative will depend on all the lower order derivative, but the dependence on these will be linear. So that the nth order derivative of y will be directly proportional to the n minus 1th order derivative of y, the n minus 2th order derivative of y, etc., the first order derivative of y as well as y itself. And the coefficient of the dependence could be a function of x. In this case, I could write it as p n minus 1 x, n minus 2 x, etc. First one as p1 x and so on. So this would be a general form of a linear differential equation in nth order linear differential equation in y. In addition to all this, it could also depend on functions of x alone, which I indicate using q of x. To write an example, we could choose the case of n equal to 2, that is a second order linear differential equation, which is one of the most commonly found type of equations in physics. And an example of this type would have the form, could be of the form d square y by dx square plus x square into dy by dx plus x cube into d x cube into y equal to some function of x. So this would be one example of a second order linear differential equation. We would largely focus on solving such linear differential equations, especially the one at second order, primarily because those are the type of equations mostly found in physics. However, it is always good to start with the simplest of the linear differential equation that we can think of, which would be one of first order, where n is equal to 1. A first order linear differential equation will have general form given by dy by dx as a function of y, something that depends on y linearly, and let's choose the coefficient minus p of x for a reason of convenience, plus some function q of x, which is usually supplied to us. Let's try and see if such an equation can be solved. Now, since this is a first order derivative of y, it is the first thing that might occur to our mind is to try and write this equation in the form of an exact equation. As we know, we have been writing exact equations of the form m of x comma y dy plus n of x comma y dx equal to 0, where m and n are functions of both x and y. It is good now to recast this equation into that form. If we try to do that, it is easy to see that I can do that by bringing over the factor of dx to the right hand side and then bringing the whole factor on the right to the left and write it as dy plus p of x y minus q of x into dx equal to 0. Now, comparing this equation with what's written above, we immediately note that m has to be 1 in this case and n has to be p of x y minus q of x. It's easy to see by at first sight that the derivative of m with respect to x will not match the partial derivative of n with respect to y, which means that this equation written as it is not an exact equation. However, we have learned in the last class what to do or how to deal with such a situation. The way to go ahead is to find the integrating factor, and in our case the integrating factor which was evaluated in the last class. We've also seen a couple of examples in the tutorials. Remember, was of the form exponential of integral of del n over del y minus del m over del x, the whole divided by m over dx. As we can easily observe that since m is 1, the derivative of m with respect to x is going to be 0, and all that this factor will involve is the integral of partial derivative of n with respect to y, which can easily be found from the expression for n. N, as it is seen, depends on y linearly, and p of x is the coefficient. Hence, if I find del n over del y, we can easily notice that that is going to be p of x. Thus, the integrating factor in this case takes the form integral of p of x dx, which is a function of x alone. Now, having gotten the integrating factor, it's good to multiply this to our differential equation and check if that indeed gets changed into an exact differential equation. So, multiplying this onto that, we get dy. It's good to write it back in the form of dy by dx into integral of, so exponential of integral p dx. That's the first term. Next term is exponential of integral p dx into p of x y minus the last term, exponential of integral p dx into q equal to 0. One could observe that the first and the second term could be clubbed together as exponential of integral p dx into y taken derivative with respect to d by dx. That's because when the derivative acts on exponential of integral p dx, we get exponential of integral p dx times the derivative of what is in the exponent, which is integral p dx, and thus we get p. Okay. So this can be written as d by dx of exponential of integral p dx, which allows us to write the first two terms together as derivative of exponential of integral p dx times 1. And the second term now could be pushed to the right hand side as q into e to the integral p dx. Now we could solve for y, the dependent variable, by integrating this equation easily to get integral p dx into y of x. On the right hand side, integral of q into e to the p dx over x plus a constant of integration c, where c is the constant of integration. So this helps us to obtain y of x as multiplying this expression throughout with the inverse of the integrating factor e to the integral p dx e to the minus integral p dx integral q to e to the p dx dx plus c into integral minus p dx. So the technique of finding the integrating factor has allowed us to solve a first order linear differential equation in general. Okay, let us look at the solution that we obtained for our first order linear differential equation and see some of its key features at this stage before going ahead with second order linear differential equations. If you look at this solution, one of the chief features that we should notice that as we had to integrate once to obtain y of x as a function of x, we ended up with one constant of integration. And in a problem where we are given p of x, q of x, and possibly p of x and q of x, in order to obtain a solution which is valid, we should also need one more quantity so that we are able to fix this constant of integration, the value to fix the value of the constant of integration c. What is that quantity? It is easy to observe that if I put a particular value for x in this equation, let's use y at x equal to x0, so that I am looking at a particular value of x that I choose as x0. Y at x0 should be obtained from the right hand side, the solution that we had obtained on the right hand side, by replacing x with x0 in every term. And when I do that, we see that on the right hand side we get things that depend on x0 whose value we know, okay, in addition to c. So let me express the right hand side broadly as some f at x0 in addition to the constant of integration c. Now, if we are given the value of this unknown at some particular value of x0, then we will be able to invert this equation and obtain c in terms of that value of y at x0. Okay. Usually, the value of y at certain x value such as x0 is called the initial condition or initial value of y. So the lesson summary is that in order to be able to use such a solution in a practical situation, we should also be given value of y at some particular value of the independent variable x, such as x equal to x0. And it is in terms of that initial value of y that we evaluate the constant of integration c. Now, this constant of integration has appeared in the process of integration, and we had to integrate this, in this case once, because we were trying to solve a first order differential equation which involved only first derivative of y with respect to x. So to solve that, we had to integrate once. So it would be expected that when you go to higher order differential equations such as second order differential equation, to solve a second order differential equation, one would be expected to integrate twice, and in the process of integrating every time, I would be acquiring one constant of integration. So in the case of a second order differential equation, since we are integrating twice, our solution will spot two constants of integration. Again, we will come to the details of this. These constants of integration will have to be evaluated if one needs the solution in a practical situation, and those constants of integration will have to be again evaluated in terms of initial values of y. And coming to the second order equation, also of dy by dx at x0. So we will see more details of this as we proceed, but it is useful to keep these general features in mind. Now we are ready to move to the next class of equations, which are second order linear differential equations. Now, second order linear differential equations are particularly of interest in physics, because in physics, most of the equations, differential equations that we encounter, be it ordinary or partial, are almost always second order in nature, especially second order with respect to time. It involves a time derivative which is of second order. For this reason, second order linear differential equations, second order differential equations in particular, and those that are linear, are of very much interest in various physical problems. So let us look at second order differential equation in a little more detail. And a linear second order differential equation usually will be stated as follows: d square y by dx square plus p of x into dy by dx plus q of x into y of x equal to sum r of x. Okay, at this stage onwards, we need to introduce certain classifications of our differential equations. And let me begin by saying those. A second order differential equation such as this is in general noted, is in general called a given a second order differential equation of this form, it is noted that we could always obtain a reduced equation out of this, which is obtained by setting the terms that does not involve the dependent variable y or its derivatives to 0. So what is the reduced equation corresponding to this? Look out for those terms that does not involve y or its derivatives, which in this case is only this. So let's set that term to 0 and write the equation as the equation so obtained is called a reduced equation corresponding to this differential equation. Now, it could be that the differential equation that we are given has no such term, in which case the reduced equation would be the same as what the equation itself would be. Such differential equations which has no term that does not involve y or its derivatives are called homogeneous. Homogeneous differential equations. And if a differential equation does involve such a term which does not carry y or its derivative, then we would term it non-homogeneous. Okay. So this is one classification that we have to keep in mind from the beginning onwards, that depending on whether there is a term that involves y or its derivatives, the equation would be termed non-homogeneous or homogeneous differential equation. And if the equation is non-homogeneous, there is always a reduced equation that we can associate with that, which would be a homogeneous equation obtained by setting that term that does not involve y or its derivative to 0. Now, why are we doing this? It would become very clear as soon as we look at the equation, the solution to such a differential equation. consider a solution of the form y. Incidentally, it is also very commonly used. Okay, the word uh, complementary equation is also very commonly associated with that equation. Now uh, let me come to the point of the solution to a differential equation of that type. Consider let consider a function y of uh, c, or let me state it as y of homog of x, which is a solution to, let's call it y of homog x, which is a solution to the reduced equation that we have here. Okay, in which case, by substituting this to the reduced equation, we would see that it solves it. Now, it is clear that if I am able to find a solution to this particular differential equation, which I will term yp of x, such that it satisfies our given differential equation, then it is observed that a general solution to such a differential equation would always be of the form y gen of x, which would be a sum of y home of x and y p of x. This can be observed by substituting this form of a solution into our given differential equation, where we immediately observe that when that part of the differential equation in which y home appears give you 0, because that is the solution to a homogeneous or reduced differential equation, and yp of x indeed goes on to solve that differential equation. So most general solution of such a differential equation would involve, in addition to ypx, which is often called particular solution of that differential equation, a part which is solution to reduced equation, which is called y home of x. So solving a second order differential equation would involve, in addition to finding a particular solution to that particular given differential equation, a part which solves homogeneous part of the differential equation also, or the reduced differential equation associated with it also. So we will get into the details of solution to such a second order linear differential equation, at least in a very limited number of cases. Okay, so in order to learn a method to solve second order linear differential equations, it is always keep ourselves narrowed down to those cases which can be discussed within the limited time, and um, and in addition to that, let us begin with the simplest of the equations that we can deal with. Okay, so keeping these two things in mind, let me say a few things about general solutions to second order linear differential equations, and let me begin with equations that are homogeneous So let me look at homogeneous second order differential equations first and try and learn a few important properties of its solutions before coming to the case of inhomogeneous or non-homogeneous differential equations. So consider a second order homogeneous equation of the type d square y by dx square plus p of x into dy by dx plus q of x into y of x equal to 0. Of course, here p of x and q of x are given functions of x, and what we need to solve for is the independent variable y as a function of x. And one comment that we can make at this point, right at this point, is that since the highest order derivative involved is a second order derivative of y, to be able to obtain y as a function of x, I should be carrying out two integrals one after the other, which will enable me to get y as a function of x. And in the process of carrying out these two integrals, I would be left with two constants of integration, and thus I would expect the solution that I get to be of the form y of x to be some constant c1 times y1 of x plus some other constant c2 times y2 of x, where c1 and c2 are the constants of integration that we just noted. A solution of this form, in a solution of this form, the constants c1 and c2 need to be found by using any possible initial data that is associated with the problem. What type of initial data can we expect in a problem of this type? Well, we had seen the type of initial data which allowed us to fix the value of a constant of integration in the case of first order differential equation. There we noted that the initial data that we obtained, we had to be of the form of value of the dependent variable y at some particular value of x, which I called x0, and that is what allowed me to calculate constant of integration, value of the constant of integration. So coming to a second order differential equation in which we have two constants of integration, what type of initial values will be needed to solve the two constants of integration C1 and C2? Well, one could be expected to be the same as y at x0, which is fairly evident that if I have y at x0, then I can evaluate at least one of the constants C1 or C2 in terms of the other. So I could possibly solve C2 in terms of C1 and y at x0, and the only one that remains to be found is C1, for which we need one more initial data. What could that initial data be? Well, if you remember where these constants emerged, they came from the process of carrying out two integrations. So if we think of C2 to be the one that came out of the second integration, which gave us y as a function of x, C1 would have come at the end of first integration, which would have reduced this equation to a first order differential equation, which would involve dy by dx, the form of dy by dx at some point of time, some value of x. So this tells me that I could use the value of dy by dx at x0 to find the first constant of integration C1. So that if I have the solution of this form, I could take its first derivative, and if the value of that first derivative is given at the same point x0, then I should be able to use that to find the remaining constant of integration, which is C1. Using such an equation. So you see that a solution of a second order differential equation which is homogeneous, such as the one given here, will involve two constants of integration, and we could solve for those two constants of integration by making use of values of y as well as its first derivative at a given point x0. So these have to be supplied along with the equations, the value of y as well as its derivative at a given point. Now given these, then the solution that we obtain have everything fixed, both C2 and C1 are known, the values of C2 and C1 are known, and that is a unique solution. There's only one such solution that will satisfy both these conditions. So that's a unique solution that we get. There's a unique solution that satisfies a pair of initial values of y and dy by dx, and that is ensured by one particular value of C1 and C2 that we obtain by solving this. Okay, the second feature that that we should note at this point is that when I wrote the solution of this homogeneous differential equation in this form, we observe that I had written down two functions, y1 of x and y2 of x. Well, there could be a question as to why I chose two such solutions and how they are dependent on each other. Is there any relation between y1 and y2? And moreover, why there are not more functions? Why did I end up with, or why did I stop with just two such terms? Why couldn't I have more functions, and so on? Well, in order to answer that question, we could again get back to the equations stated here, which are the initial conditions of the equations. Usually these are called the initial conditions or initial values. Suppose out of the two solutions y1 of x and y2 of x, I were able to write one of them as a multiple of the other, such as y2 of x is some constant times y1 of x. If this were the case, then one could observe the following, that by taking a solution of this form over there, I would end up with only one constant of integration to solve for. Okay, substituting this there. So let me choose this constant, which is a multiple, which gives y2 as a multiple of y1x to be k, so as to distinguish it from the remaining constants, and substitute into that solution. That makes the solution y of x to be c1 of y1 of x plus c2 times k into y2 of x. Together it makes it c1 plus c2 times k into y2 of x. Well, this whole thing c1 plus c2k is a constant, which I could very well relabel with one single constant. Let me choose it as c b of y2x. Well, this is not y2, this is y1. B of y1x. Sorry, not the no, sorry, not, yeah. Note the change that I had made a mistake in writing it as y2. It should be y1 at both these points, and the final form should be b of y1. Now, if I were able to do this, this shows that if I were able to write y2 as a multiple of y1x, then you really have only one constant appearing in the solution, which is not the case that we expect in a solution for a second order differential equation. For a second order differential equation, we would really need two constants of integration, one emerging at the end of every integration. So it's clear that such a thing is not possible. So one could say that y2 of x has to be independent of y1 of x, or more precisely must be linearly independent of y1 of x. Well, so it's clear that we have to have at least two solutions. Now, we could go ahead and ask, could there be more? Could there be more than two? Well, if we had to have more than two independent solutions that make up general solution to a homogeneous second order differential equation, then we had to have more constants of integration also, without which this wouldn't happen. But that is not the case for a second order differential equation, because we only integrate twice in order to reach a solution, and we cannot obtain more than two constants of integration in the process. So this argument, which is not a very rigorous argument, indicates that solution to a differential equation which is of second order would involve two linearly independent functions, and extending this argument to higher order differential equations, we could claim that an nth order differential equation would have solutions that are would have n solutions that are n solutions that are independent of each other linearly independent of each other. In fact, this provides also a test as to whether two given functions which we expect to be a solution to a certain differential equation are independent solutions indeed. Suppose we are given two solutions, let's call it y1 of, let's call it y1, two test solutions, y1t of x and y2t of x as the solution to the differential equation we just had, such that each one of them solve the equation given. Okay. So both y1 and y2 solve this, which I indicate using the notation y1, yt1 and yt2. Okay, to check whether the given test solutions are linearly independent pair, let us write a general solution by making use of these two, which should be of the form that we had seen, y of x as c1 times the first test solution v1t x plus c2 times the second test solution y2t of x. Since the general solution is of this form, it is expected that any given initial values of y of x and its derivative at some point x0 must satisfy those equations given in terms of y1t and given in terms of the values of y1t and y2t at x0 in this form. And again, for the derivatives, dy by dt at x0 equal to c1 times dy1t by dx at x0 plus c2 times dy2t by dx at x0. So if these indeed give a solution, then that such a solution must satisfy the given initial conditions for y at x0 and dy by dt at x0. And that should help us to solve the constants of integration as we claimed, which are C1 and C2. But notice that the values of y at y1t at x0 and y2t at x0 and dy1 by dt, dy1 by dx at x0 and dy2 by dx at x0 are certain numbers which we could obtain by putting values of x0 to both all these functions, and thus these equations that I obtain are a set of simultaneous algebraic equation in unknowns C1 and C2. Okay. So let me write this claim that these equations are simultaneous equations which are algebraic equations in C1 and C2. And we know when we should be able to solve such a condition to obtain C1 and C2 in terms of all the remaining values, and that condition is when I can invert this relation to calculate C1 and C2, and that inversion would happen only if when I write this as a matrix equation with y1t x0, y2t x0 as its first row and dy1 by dx at x0 and dy2t by dx at x0, multiplying C1 and C2, giving me y at x0 and dy by dx at x0. I am able to invert such an equation to obtain C1 and C2 only if the determinant of this matrix is non-zero. The determinant of that matrix, as you can see, is y1t x0 into dy2 by dxt at x0 minus y2t at x0 into dy1 t by dx at x0 is not equal to 0. So this matrix is often called Wronskian matrix, and the determinant is very often called Wronskian. So this quantity is often indicated with letter W, which is after the word Wronskian. So we can say that only if the Wronskian for the two solutions is non-zero, we could consider the two solutions as independent solutions. Okay. And what is interesting is that if the Wronskian of the two solutions are independent or is non-zero, then for any given point where in the region where the differential equation that we are considering is valid, then it is assured to be true for all points in that region. Okay. So now we are ready. Now we are at a point where we could go ahead and look at solutions to second order linear differential equations which are also non-homogeneous in nature.